Welcome to our July session of Colloquia in the Galaxies Model Group Colloquium series. Today's speaker is Rodrigo of Flores-Freitas. He has acquired his bachelor degree in physics in 2021 at Universidad Federal do Rio Grande do Sul. During his undergraduate research project, he studied compact galaxy, which focused on Relic galaxies. He is now on his first year of PhD at Universidad Federal do Rio Grande do Sul, studying groups of galaxies using simulation and observation. The title of his presentation is Relic Galaxy Analogues in Illustris TNG50, the formation pathway of surviving red nuggets in cosmological simulation.
Thank you, Ramiro. Thank you, Maria Emilia and Candela for the invite for this colloquium. And I did this work with my former advisors, Ana Kia Santos, Cristina Furlaneto, and with collaboration of Professor Maria Emilia de Rossi and other collaborators. And the title is already here, as you can see. The focus of this work was to compare simulations and observations and understand the formation of Relic galaxies. So, giving a brief introduction, we know that galaxies are distributed in bimodal, following a bimodality in various properties, such as color and morphology. The early type galaxies are generally more massive than the late type galaxies. And these early type galaxies are the focus of this work. We want to understand how they form and what are the processes that form their most inner parts. These early type galaxies, it is known that they scale their mass with their sizes. Here is the effective radii versus the stellar mass, and that this relation with size and mass evolves with time. So it's important to understand the structure of these early type galaxies, how they form their outer parts and their inner parts. So that's the main question in the background of our work, how massive early type galaxies form. And there is a very well-established or popular scenario in this particular literature, which is called the two-phase formation scenario. Basically, in the first phase of this scenario, there is formed a very compact and massive core in high redshift through energetic regime that is dissipational. So the stars are form a very dense core. And after the creation of this first core, which is sometimes called red nugget, when observed in high redshift, there is the creation of the outer parts of early type galaxy, like this one. This second phase is drawn to dry mergers with another smaller galaxies that do not have too much gas and which is more conservative in its energetic regime. So it forms the more puffy outer parts of the ETGs. So basically, this is the scenario, and the relic galaxies that it's the main topic of our work are formed when we don't have these other parts, the second phase. So the galaxy forms this very compact nugget in high redshift and remains almost or completely unaltered to today, redshift 0. So there is already relic galaxies identified in the local universe. Here I am showing one of them, which is, I think, the most famous, NGC 1277. And they are, as expected from this scenario, compact with this range of effective radii, massive, very massive, and they have a dominance of old stellar populations, very old. And it is suggested that they are the local analogues of this kind of compact galaxy observed in high redshift. So today we have at least 13 nearby Relic galaxies already found and studied in different studies. And there is also a recent survey that is looking for more Relic galaxies in higher redshift, up to 0.5, which is called the INSPIRE survey. Now going to our work, we have some objectives, some goals for this work. The main one, the first one was that the question that if cosmological simulations can generate Relic galaxies, which are rare objects. So it's a reasonable question to test the cosmological model employed in the simulation, and also the baryonic physics. The second question is if we can find something similar to Relic galaxies in the simulation, how far their properties agree with the real relics, how far we can compare these relic analogues in the simulation with the real relics. And then we go to other questions that are useful when we are using simulations that is to see how a relic galaxy analog can be formed in the simulations, and also if the environment of these objects play an important role. And here I am putting a TNG image and a Hubble Space Telescope image because we want to join the observational and cosmological works, the numerical and observational works. Our observational sample is composed of 13 galaxies that were observed with HST, the Hubble Space Telescope, and their data are available in this archive. They were observed in 2016, I think, and Rodrigo published this work in 2017. There we have data from the infrared in this band, a fairly reasonable exposure time, so we can see very well the structure of these objects, and the pixel scale is this one. We also get another information from literature and the NED extragalactic database. And regarding the simulations, we use the Illustris TNG, which is a very recent simulation. It's fairly high resolution, and it's included many types of physics, magnetic fields, the basic gravitational interactions, the baryonic physics, enrichment of the gas, and etc. We choose the TNG50 simulation inside the TNG suite because it has a high spatial resolution. Here we consider the spatial resolution comparable to the 3 times the softening length, gravitational softening length, and it has a high mass resolution, having this mass for the smaller stellar particle. There is some disadvantages for using this suite because it's a fairly small volume, but we have to equilibrate the two things when we have to work with simulations. Regarding the data of the simulations, it's a very data-intensive work. We use the Jupyter Lab provided by the TNG team, which we can work with snapshot data, the group catalogs, merger trees very easily, and without the need to download the data to local computers. But we also download some supplementary catalogs and specific parts of the snapshots to do specific analysis. We use a lot of different Python packages, and we develop our own module to work with some specific parts of the simulation. We also post-processed the particle data from the simulation using the SCRT radiative transfer code to create images, mock observations of Hubble Space Telescope using the same band, pixel scale, and exposure time for the observations that Ildrin did in the previous sample that I showed before. So we started by looking at the catalogs of the simulation, looking first for massive, compact, and quiescent galaxies. These are the basic properties of a Relic galaxy in redshift 0, or close to 0. So we use different criteria, different apertures, different separations in size, and different quiescence criteria. Then we join all these galaxies that we can find using different criteria to be very comprehensive. And the total number of Relic analog candidates was 48. Here I am showing just a figure of effective radius versus total stellar mass, because it is known that the Relic galaxies in redshift 0 are outliers in this relation, being more compact for their masses. Also, for these 48 galaxies, we wanted them to be old and have no sign of interaction or recent interaction. So we analyzed their stellar populations of these galaxies and imposed that the minimum of 75% of the stellar mass must be older than 9.5 gigayears, which is reasonable for the Relic galaxies. And we also analyzed the stellar density maps of these objects to see if there was no stellar string or close companion interacting with it. After this final selection, only 5 candidates survived, and here I show them and some of their properties: the age, the size, and their mass. The properties of these 5 candidates at redshift 0, starting by their metallicity and this abundance that gives a proxy to the alpha enhancement, is this. We have here in the x-axis the mass, and in the y-axis the chemical properties. In the first panel here in the metallicity, we can see that all the candidates are more metal-rich than quiescent galaxies in the simulation, with the orange dots here representing the quiescent galaxies, and this line here representing the median for the quiescent galaxies. So all the candidates are more metal-rich, which is expected for the enrichment of Relic galaxies. We also can see that this proxy of alpha enhancement shows that these 5 candidates are also very alpha enhanced compared with the typical quiescent galaxies of same mass in the simulation. This gives an idea of how fast the star formation was in these galaxies. The spatial distribution of metallicity we can see here by these profiles. 2 of the galaxies, I draw your attention here, the red one and the green one, have supersolar metallicity up to 6 effective radii, about 10 kiloparsecs, and are very old. Also here we have the age profile, are very old, up to 6 effective radii and beyond, older than 11 gigayears. So they are very good candidates for Relic analogues. We also analyze the stellar structure of these objects to see if they match it on the properties of real relics. here I show the stellar to dynamical mass inside one effective radar. This is a measure that Yildering and other authors did for Relic galaxies to see how the stellar mass dominates in the center of these objects. And here we see the fraction of the green and red galaxies in our sample being very high, about 80%, which is similar for the median of Yildering in 2017, which is about 89%. So it's a good sign that these objects can be good relic analogues. Here I also show that these objects are very dense. In the y-axis, it's the surface density inside one effective radii versus stellar mass. And as expected, these objects are very dense. We also look at the light distribution of these 5 relic analog candidates in the simulation and compare with the real galaxies. The first thing that we notice is that the galaxies in the simulation have lower concentrations. It means that their inner parts are not so cuspy when compared with the real galaxies, but that some of them have at least rough similarity in the shapes of the isofolds, such as subhalo 6 and subhalo 366407, which have this disky shape. Looking at the brightness profile of these objects, there is a rough agreement beyond 0.9 kiloparsec, but in the inner parts, as we could see in the images, there is disagreement between the simulated galaxies, relic analog candidates, and the real relic galaxies. The real relic galaxies are more cuspy than the simulated galaxies. We discussed this a little bit, and our best guess is that it's an effect of the gravitational softening in the simulation. This band here, this blue band here, shows the region in which the forces between the particles in the simulation are not Newtonian, because here the softening dominates. So maybe this is an effect of the softening, since here we start to see a greater disagreement. We also look at the kinematics of these objects. We projected their stellar velocities in different orientations. And we see that all of them have signs of rotation, very clear signs of rotation, which is expected for relic galaxies, for the galaxies that we have in our observational samples. We also look at the velocity dispersion of these objects, especially the central velocity dispersion of these objects, which is expected to be high. In the real galaxies, they go beyond 250 kilometers per second. And in the simulation, we see only 2 galaxies reaching at least 200 kilometers per second, which is this one and this one. In the center, they reach the peak. The central sigma here is above 200 kilometers per second, which is in more concordance with the relic galaxies kinematical maps. These other 3 here, not so much. So the final question that we have after analyzing all the properties of these objects in the simulation is if there is any good relic analog in the TNG50. So we reached the conclusion that subhalo 6 may be the best analog, given a set of properties. The first one is that this object, there is no significant star formation in the last 9.5 gigayears, which is about 1.5 in redshift here. And here I show the fraction of the mass that is dominated in this redshift. It's about 97.4%. It's older than 9.5 gigayears. These galaxies are this subhalo is uniformly old, up to 6 effective radii. Here we see the age profile of this object in the simulation. And here is the age profile of 3 Relic galaxies. And they also show this more or less flat age profile, which indicates that it formed almost all of its stars in the very short period of time and very long ago. They also are supersolar, very enriched in metals, up to 6 effective radii, which is also expected for the Relic galaxies in the observations. They have isophotes with roughly similar shapes to this galaxy. Have isophotes with similar shapes to real Relic galaxies, the more disky shapes. The galaxy also have a high stellar to dynamical mass fraction. For the galaxy in the simulation, it's about 84%, while for the median in the observational sample, it's about 89%, which gives an idea that the stellar distribution in this galaxy is similar to the real galaxies. It shows a clear rotation pattern as expected. Also has central velocity dispersion above 200 kilometers per second in different orientations. And there is a peculiar similarity of this object with the most famous real Relic galaxy, that is its environment. This galaxy in the simulation is in a very dense environment, is in the most massive cluster of the simulation. And it is suggested in the literature that Relic galaxies prefer dense environments. And GC1277 is one example of this. So it's a peculiar similarity with the real Relic galaxy. There is also another galaxy in the simulation that may be a good analog, but it has a contamination of young stellar populations. As you can see here, it's very small. It's about 1%, but it's very recent, so it would be not fit in a scenario of a Relic galaxy almost untouched in its stellar populations. So we call this galaxy contaminated analog, or not so good Relic analog. Then we did a brief analysis of the number density of these Relic objects in the simulation. Previous works that were theoretical and observational reach about this value of number density of relics based in semi-analytical models and some observational, incomplete observational. For our observational sample, if we take the sphere in which they are lying in our local universe, we get this number density, which is a little higher, because actually this value is a lower limit for the number density. And if we consider our results for the simulation, we find roughly the same value for one Relic if we consider just the best analog, and about 1 order of magnitude higher if we consider the 2 Relics that we found. So these are the main results regarding Relic number density, but we do not make further calculations, consider the completeness of the observational sample. So it's just a brief analysis. And finally, the interesting part of the analysis is the formation and evolution of these objects. So we analyze the history of these objects in the simulation to see how they form, how they interact with their host halo, and etc. And for subhalo 6, the best analog, we can see here in this panel the mass in different components, gas, stars, and etc. And the look back time or redshift. And we see that this gas, this galaxy lost its gas in orange here when almost the same time it enters its current host cluster. So it probably has its gas stripped and didn't have any further star formation as it orbits the center of the cluster. The other galaxy retained its gas, but it did not show any strong star formation in its history here, in its star formation history. It is a central galaxy in its halo, but it is in a low density environment. And we can see here in this gas animation that this galaxy formed a ring of gas in redshift about 0.25. So it accreted more gas later. We also look at briefly at the formation conditions of these objects. We look at the halo mass in which this galaxy is born at redshift 4, sorry, and the gas fraction. And we can see that both best analogues born in relatively massive halos when compared with quiescent galaxies of the same mass in redshift 0. So these galaxies were already in relatively massive halos at high redshift. The total gas mass fraction differs for the two best analogues, but what we can see is that subhalo 366407 already had a low gas fraction in its halo very early. So finally, we discuss possible environment effects in the formation of Relic galaxies. These two objects are in very different environments, the subhalo 6 and 366407. Subhalo 6 is very close to the most massive cluster in the simulation, while subhalos, this other subhalo, it's in a low density environment. In this case here, the gas may be stripped, so the galaxy will have no fuel for further star formation, and here the gas may be pushed away, maybe some effect of AGN or other complex effect, but this requires a further analysis of the dynamics and thermodynamics of the gas in these objects. So finalizing the talk, here are the conclusions. The first one is that we can find at least one good relic analog in TNG50. It has similarities with a real relic galaxy, especially in its environment. There is possibly another analog given a degree of relic, admitting that it can have a small contamination of relatively young stellar populations. The central structure of any of the analog in the simulation is not the same of real galaxies. It's less dense than it should be. And the number density that we find in the simulation is comparable to observational estimates, but it's a little bit overestimated. But further work needs to take into account the completeness of the observational sample. And regarding the formation and evolution of relic galaxies in the simulation, basically they born in massive dark matter halos. They have an early star formation and merging before redshift 1.5. They cease their star formation, and further they have their gas stripped or expelled, maybe temporarily, and also there is no further star formation. So here are the conclusions. Here are acknowledgement to some people that helped in our work, and thank you.